Good morning once again. Welcome to the day 5 of the chemistry class, chapter 6, chemical thermodynamics. Today is 17th of November. Now, in my previous class, yesterday's class, I talked about entropy changes in isothermal expansion of a gas. And I also showed you for that entropy changes in isothermal expansion of a gas, where I told you to remember this formula. Delta S is equal to 2.303 nR log to the base 10 V2 by V1. It is isothermal, so the temperature will not be there. So this formula you have to remember for entropy change in isothermal expansion of a gas. Okay. Now today I am supposed to discuss with you all entropy changes happening in phase transformation. Entropy changes happening in phase transformation. So please pay attention. Okay. Entropy changes happening in phase transformations. Now, what is the meaning of this? Now, phase transformation means change of state from solid, say solid to liquid, or liquid to gas, or gas to liquid, and liquid to solid again. This is called phase transformation. That means you can say in short, the change of matter. The change of matter from one state to another state is called phase transformation. Now, under this phase transformation, we'll be learning about the various and what you call entropies. Like there are entropy of fusion. The first one which I will discuss is it is called entropy of fusion. It is called entropy of fusion. Now this entropy of fusion means what? This means change in entropy. This means what? Change in entropy when 1 mole of a solid substance. This means change in entropy. Change in entropy when 1 mole of a solid substance substance transforms into the liquid form. Transforms into liquid form. Now for this, I will write down the formula delta FUS and over here S. This means entropy of fusion. Entropy of fusion is equal to entropy of the liquid minus entropy of the solid. Now this S stands for entropy. So entropy of fusion means change in entropy when 1 mole of the solid transforms into liquid form. So here that's why we're writing delta S fusion is equal to entropy of liquid minus entropy of solid, and this will be equal to, remember the formula, delta H fusion, enthalpy of fusion divided by Tm. This is T stands for temperature, the melting temperature of solid in Kelvin. Okay, and remember this delta H fusion. This delta H fusion is enthalpy of fusion. Enthalpy of fusion per mole and this Tm means melting temperature of the solid. Melting temperature of solid. Okay, so this is entropy of fusion. The next entropy, that is number 2, the next entropy is called entropy of vaporization. It is called entropy of vaporization. So what undergoes vaporization? Generally liquid undergoes vaporization. So entropy of vaporization. Entropy of vaporization means, what does this mean? It means the change, the entropy change. The entropy change. Entropy change when 1 mole again, when 1 mole of a liquid, 1 mole of a liquid, 1 mole of a liquid changes into vapor, vapor at a temperature, at its boiling point, at its boiling point. So this is the definition, entropy of vaporization, and its formula which you have to remember is delta S vaporization, VAP, vaporization is equal to entropy of the vapor minus entropy of the liquid, that is equal to change in enthalpy of vaporization, VAP, divided by TB. This delta H H means enthalpy of vaporization, enthalpy of vaporization per mole, and this TB stands for the boiling point in Kelvin. So this is the second entropy change in phase transformation. Okay, then the next one is number 3.
Sir,
Yes,
so the entropy of fusion also takes place at melting point.
entropy of fusion. This one, it takes place at just a minute. Yeah, melting point. Correct. It's melting point only.
Yes, sir.
The other one is boiling point. Boiling point. This one is melting point, but I'm calling it melting temperature. Okay, it's same thing. Melting temperature and melting point is same thing. Okay. The number 3. The third one is called entropy of sublimation. It is called entropy of sublimation. Entropy of sublimation. Now, in this entropy of sublimation, remember it is defined as uh, change in entropy, change in entropy, entropy involved, involved, involved in the transformation, in the transformation, transformation of a solid directly, directly into vapor, directly into vapor at a particular temperature. So this is entropy of sublimation is whenever there is a solid changing directly into vapor or a vapor changing directly into a solid. Both ways it is entropy of sublimation. So now for such situations we write the formula as delta S sublimation is equal to entropy of vapor, that is the final state, minus entropy of solid, that can be written as delta H sublimation divided by temperature, whatever the temperature is required. Okay, so delta H sublimation is enthalpy of sublimation and the temperature is in Kelvin. Okay, now these were the 3 types of entropies for phase transformation. There is one more. There is one more, not under this heading, but it is under a separate heading, which is called entropy change in chemical reactions. Which is called entropy change. Which is called entropy change in chemical reactions. Chemical reactions. Now we know in a chemical reactions, the reactants, if there's a chemical reaction A plus B, it is giving C plus D. So these are the reactants, these are the products. These are the reactants, these are the products. So in such a situation, the formula for entropy change in chemical reactions, delta S is equal to sum of the entropy of the products minus sum of the entropy of the reactants. This is the formula you have to remember. Now, if this entropy change for chemical reaction is happening at 25 degrees Celsius, the standard temperature. So if the reaction happens at 25 degrees Celsius means 298 Kelvin, and the pressure is 1 atmospheric pressure, then the same thing we write it as delta S naught, the standard entropy change. This is not, we pronounce it as not, NOT not. Delta S naught becomes sum of the entropy of the products not minus sum of the entropy not of the reactants. So this is the standard entropy change for a chemical reaction is equal to sum of the standard entropy of the products minus sum of the standard entropy of the reactant. Standard. So this is called standard at a temperature of 25 degrees Celsius. That is very important. Now let us talk about a general case. So if we take talk about a chemical reaction, a chemical reaction, say we have a chemical reaction where the stoichiometric coefficient is small a, reactant is capital A, small b, capital B, it is giving small c, capital D plus small d, capital D. If you consider this reaction, then at standard conditions, you can write delta S naught is equal to sum of the standard entropy of the products minus sum of the standard entropy of the reactants. Okay, now here if you put further, if you try to work on this formula further, then we can write delta S naught is equal to small c, okay, into entropy of the, that is C, that is over here, this one is a CC, okay, this one is CC, the reactant plus D, entropy D over here, minus A, entropy, standard entropy of reactant, that is A plus B, entropy of the reactant, this way. So this is also one way of representing this formula. Okay, this which you see over here, this may be there or may not be there, you can exclude it. Okay, but you can remember this much only. Okay, formula for entropy change in chemical reactions. Now this was the entropy change in phase transformation and entropy change in chemical reactions. So this the idea of this formula will be clear only when we do one or two numericals based on this formula. Now the next topic which we are supposed to discuss, it is called thermal death in thermodynamics. Now what is thermal death? Now uh, we know that entropy remains constant in reversible process. So in a reversible process, what is there? In a reversible process, in a reversible process, entropy is constant. S is constant. You know that. But it increases in an irreversible process. So in an irreversible process, process S increases. S increases. So I was talking about thermal death over here. The entropy in a reversible process, the entropy is constant. Okay, but in an irreversible process, entropy increases. This we already know. Moreover, in nature, most of the processes are spontaneous, which are irreversible in nature and involve an increase in the entropy of the system. Therefore, we know that entropy of the universe is continuously increasing. Now, the increase in entropy means an increase in the disorder or decrease in the order energy which is available for doing useful work. Okay, so since the entropy of the universe is increasing day by day, because universe, whatever changes are happening, all are irreversible. A stage may come one fine day when there will be no energy available for useful work. Okay, so that time all affairs will totally paralyze our activities and life will come to a standstill. Such a state of affairs will correspond to thermal death of the inhabitants of the universe. So this is one important concept which has been beautifully explained in this chapter. So here, with regard to thermal death, remember the entropy of the universe is what? Increasing. So as the time goes by again and again further ahead, a time might come a time might come when all the available energy is exhausted, and there is no energy which is useful left. So that time, what will happen? All the activities will come to a standstill, and in such situation, all the affairs, all the day-to-day activities will correspond to what is known as thermal death of whom? Because of the inhabitants of the universe. So this is called thermal death. So this is one thing you have to remember on the basis of irreversible process. As the entropy is increasing, what is happening? Slowly and steadily, all the available energy which is there for doing useful work will get exhausted, and then everything becomes standstill. That is called thermal death. Okay. Now, now after this, there are some numericals, very simple numericals based on the formula, direct application of the formula. Okay, so for the numericals, you can have a look at your textbooks, the new textbooks, page number 300 and say after 300 and this is 381, page 381. Look at this example, example 6.11. Example 6.11. The question says the enthalpy change for the transition of liquid water to steam. Liquid water is changing to steam, that is vaporization is happening. The enthalpy change, that is delta H vaporization, is 40.8 kilojoules per mole at 100 degrees Celsius, means 100 plus 270, that is 373 Kelvin. They are saying us calculate the entropy change for the process. So first, read the question carefully and write down what is given. Delta H vaporization is 40.8 kilojoules per mole. TB, the boiling point for liquid to change into steam, it is given 100 degrees Celsius, that becomes 373 Kelvin. The entropy of vaporization is given by the formula which I have already stated before in my previous slides. Delta H vaporization by TB. So put the values over here and you will get the value of entropy of vaporization. Entropy of vaporization. So it is coming to 0.10938 kilojoules per mole per Kelvin. So you can convert this into joules only simply by multiplying by 1000. So you get 109.38 joules per mole per Kelvin. Answer. Direct application of formula. Okay. So you should be able to do these sums. But to do these sums, it is very important that you remember this formula. And by reading the question, you should be able to figure out what type of change is happening, whether it is vaporization or whether it is fusion or whether it is sublimation. Okay. Now look at the next example, example 6.12. Example 6.12. The following data are given for melting point. Melting. Melting means what? Fusion of potassium chloride. Delta H, delta H fusion for potassium chloride is given 7.25 kilojoules per mole, and delta S fusion for the same is given as 0.007 kilojoules per mole per Kelvin. Calculate the melting point. So that means to find the value of TM over here. Direct application formula. So delta S fusion is given Delta H fusion is also given. Tm is supposed to be formed out. Now this is given, so we'll put the values over here directly. Okay, so Tm I'm getting 103735.7 Kelvin. So don't you think these sums are very easy, provided you know what type of changes, what type of phase transformation is taking place. Now, do you think you can do such sums for examination? Because this will be given in the multiple choice question in the final term examinations, okay, which is going to be held very soon, okay. And your final term chemistry paper, annual term chemistry paper, it's a promotion examination. Chemistry, it's on the 9th of December. It is on the 9th of December. Please check the routine. Okay, it was posted in the class WhatsApp group also. Okay, now that was example 6.12. There is another example 6.13, chemical reaction. Entropy change in what? Chemical reaction. So there is a chemical reaction. The question says calculate the entropy change delta S naught for the following reaction at 25. Whenever the temperature is 25 degrees Celsius, it is called standard entropy change. Okay, so sulfur dioxide gas reacting with oxygen to give sulfur trioxide gas 1 mole. Okay, the absolute entropies at 25 degrees Celsius and 1 atmosphere pressure for sulfur dioxide, oxygen and sulfur trioxide is given to 48. These two are reactants and this is the product. So all the absolute entropies are given to 48.5, 205.0, 256.2 kilo vertical joules per Kelvin per mole respectively. That's very easy. So here also it is directly application of formula. Delta S naught is sum of the standard entropy of the products minus sum of the standard entropy of the reactant. So we write the formula, and for this equation delta S naught becomes equal to S naught into SO3. This is the product minus the reactants. We put S naught in the beginning over here, and then we know this is given uh, 256. If you put the values over here, SO3 256.2 minus 248.5, okay, plus half of this oxygen, no? Because it is over here, stoichiometric coefficient is half, so we put half over here, okay, and then simplify this, we get the answer 256.2 minus 351, we're getting negative. The value of entropy, it is coming negative. So what does a negative value of entropy change mean? Is it an endothermic reaction or an exothermic reaction? Tell me. Is it an exothermic reaction?
Endothermic.
Huh? It
So
is negative.
endothermic.
It is negative. Delta S is negative. Delta S
So
is
sir, exo.
delta S. I'll just revise. I'll just go up. Okay, just a second. You might have, it's confusing, but it's important to practice it several times. So if you look over here, delta S not negative. It is non-spontaneous process. It is non-spontaneous process, which means heat. It is what? It is what? Absorbing heat or releasing heat. Just a minute. I'll come to the main point over here for delta S. Sign convention I discussed in one of the previous classes. Just a second. In the first law of thermodynamics is there. First law of thermodynamics. This reaction is requiring what? It is giving out heat. It is giving out heat. So entropy for whenever it is heat is given out, it is negative. So this I done when I did the first law. Sign convention. See, over here, work is done on the system. W is positive. So if you are doing work on the system, then W is positive, but the entropy, the disorder in the system, what is happening? It is increasing, no? It is increasing. This is one sign convention. Just a minute. Heat absorbed by the system, Q is positive, but heat lost by the system, Q is negative. If the system is losing heat, then entropy is becoming lower, no? Entropy is becoming lower, system is losing heat.
Yes,
That
sir.
means that is an exothermic reaction. So from this concept, I am talking about entropy. If the system is losing heat, Q is negative. That is an losing heat, giving out heat, exothermic reaction. So entropy becomes negative in this case. So that is what I was trying to tell you over here. That is from the first law of thermodynamics. Okay, so we come back to our page over here and try to what do you call discuss the next topic in this chapter, which is called work function, which is called work function. Let us come to this page, work function. This is already done. Work function. Just a second. Yeah, yeah. Work function. It is called. It is named after the person Helmholtz. Helmholtz. The Helmholtz free energy. It is also known as work function. It is represented by capital A. Now let us first understand what is the meaning of this work function. Okay, but before that, let us try to keep this formula in our mind. This formula, only this formula. Okay, this much. This formula A is equal to U minus Ts. U stands for internal energy, T stands for the temperature, S stands for the entropy, and this capital A stands for work function. Okay, now this work function is the free energy. Now it is the energy over here. Helmholtz free energy is a function of state. That is, a change in A depends upon the initial and final states of the system. So we are trying to understand Helmholtz free energy now. So if you subtract the product of the temperature and entropy from the internal energy, that is U, that is called work function or Helmholtz free energy. Okay. Now suppose a system transits, it changes its state from state 1 to state 2 at a temperature which is constant. So let the three functions in equation 6.49, the three functions in equation 6.49 in state 1 be A1, U1 and S1 because T is constant, and let their values in state 2 be A2, U2 and S2 respectively. Thus, according to these two states, we can write down two equations for state 1, one equation, A1 is equal to U1 minus TS1, and then for A2 we can write U2 minus TS2 for state 2. Upon subtracting, the change in free energy delta A can be written as A2 minus A1 or U2 minus TS2 minus U minus TS1, or if you rearrange this you get U2 minus U1 minus TS2 minus S1. So we have over here delta A. The change in Helmholtz free energy is equal to delta U minus T delta S, where delta U refers to a change in the internal energy and delta S to a change in entropy. Now, why we are talking about free energy, Helmholtz free energy, and maximum work done by the system? Okay, so if the change under reference is reversible at constant temperature T and the heat absorbed is Q reversible, we have delta S. We know this already from before. Delta S is Q reversible at temperature. So if you substitute this equation 6.3 for this one in equation 6.49 in the previous equation, we have delta this A is equal to delta U minus Q reversible, because Q reversible is equal to T delta S. We have seen over here T delta S. Okay. Now, from the equation of the first law of thermodynamics, we know delta U is equal to Q plus W. So we put over here for reversible process, W reversible is equal to delta U minus Q reversible. Okay. Now, if during the change under consideration work is done by the system, if the work is done by the home system, then it is minus W reversible is delta U minus Q reversible. Now, comparing equation 6.51, compare this equation and this equation. If you compare this is same. So we can say minus W reversible is equal to delta A. So we have minus delta A is equal to W reversible. Therefore, since the process is carried out reversibly, W reversible represents what? Maximum work. So the maximum work done by a system is equal to negative of the change in Helmholtz free energy. So we can say thus the decrease in Helmholtz free energy. That means after doing some work, if I need to lift up a pen, lift a pen or a bucket full of water, I might be applying the same energy to lift a pen and lift a bucket of water. But if I lift a pen by using the same energy, lot of energy is wasted as free energy, which is not utilized to lift the pen, because the amount of energy required to lift a pen can be very very less, negligible. Okay, so that is what I'm trying to talk over here, Helmholtz free energy. So if there is a decrease in the Helmholtz free energy function A in any process at constant temperature, it can be regarded as a measure of the maximum work done by the system. So that means there should be a decrease in the free energy, then only there will be maximum work that will be done by the system. So on this basis we come to a very very important concept which is called Gibbs free energy. Okay, now what is Gibbs free energy? The Gibbs free energy, we can say it is the energy which is available to do useful work, which is available to do useful work. So we can talk about Gibbs free energy. A spontaneous process involves an increase in the entropy of the system. We know that, and proceeds first towards equilibrium. Thus, a spontaneous process proceeds in the direction in which delta H system entropy change of the system is maximum and delta H enthalpy change in the system is minimum. We have already seen that neither a negative value of delta H nor a positive value of delta H system alone can be taken as the sole criterion for spontaneity of the process. However, as suggested by the second law of thermodynamics, we know delta S total is equal to delta S system plus surroundings can be used to predict the spontaneity of a process. For a spontaneous process, delta S total is always positive. Remember that. The determination of delta S total requires determination of delta S surrounding, which is not always possible. Hence, to clear this confusion, a new thermodynamic function, which is known as Gibbs free energy, was introduced to explain the spontaneity of a process, and which we obey even till today. So, Gibbs free energy and free energy change. Gibbs free energy is a very important thermodynamic function, and it is represented by capital G. It was introduced by J.W. Gibbs, defined as, learn this definition of Gibbs free energy: the maximum amount of energy available to a system. To whom? To a system. If I am a system, then available to me. So the maximum amount of energy available to a system during a process for doing useful work under constant temperature. Temperature is constant, and pressure conditions. Pressure is also conditions. It is constant. It is called Gibbs free energy. So the maximum amount of energy available to a system during a process for doing what? Useful work under constant temperature and constant pressure conditions, it is called Gibbs free energy. That is the definition. So on the basis of this definition, we can also work out similar relationship as we have worked before. So we shall study the concept of this useful work and the meaning of the above definition in a bit later in this section. Mathematically, this relation derivation is not required, but learn this what you call equation. The equation relation is like this: G is equal to H minus Ts. Like like A is equal to H minus Ts. Here also we have for Gibbs free energy G is equal to H minus Ts, where H is the enthalpy of the system and S is the entropy of the system, and T represents the temperature, which is constant in Kelvin scale. Now, looking at the Gibbs free energy change, we know it is a state function. Therefore, the change in Gibbs free energy depends only upon the initial and final state. So, keeping all this in mind, if you write down the Gibbs free energy once again and substitute instead of H U plus PV, we get a relation G is equal to U plus PV minus TS. Or the change in Gibbs free energy can be expressed as delta G is equal to delta U plus delta PV minus delta TS. Or delta G is equal to delta U plus P delta V. Pressure is constant, that's why P. There is no delta P. P delta V plus V delta P minus T delta S and S delta T. Temperature is constant, so this will go out. Delta T will go out, delta P will also go out. This will be 0. Delta T is 0, delta P is 0. So this will become 0. This 2 will become 0. And after that we have, substituting the values, we have delta G is equal to delta U plus P delta V minus T delta S. And since we know delta H is delta U plus P delta V. That's why delta U plus P delta V becomes delta H. So we have finally delta G is equal to delta H minus T delta S. So this equation 6.58, remember this equation, represents the free energy change in a process occurring at constant temperature and constant pressure, and is known as Gibbs Helmholtz equation. Now, this equation is going to help us understand the spontaneity of a process. How? Let us have a look further. So, there's a relationship between this Gibbs free energy and Helmholtz energy also derived. Derivation is not required. So, remember over here, delta G, equation 6.61, only the final equation is equal to delta A plus P delta V. So, this is one relationship between Gibbs free energy and Helmholtz energy. After that, coming to the next page, the net work done by the system and Gibbs free energy change. We know delta G from is equal to delta A plus P delta V from above, equation 6.61. Okay. Now we know for the maximum work done by the system, delta A has to be minus W. So if you compare equation 6.62 and 6.63, we have minus delta G is equal to W work done minus P delta V, which means the quantity W minus P delta V is the maximum work obtainable for a system other than that due to the change of volume. So if you look at this, for the maximum work obtainable, there has to be a decrease in the Gibbs free energy. So please underline this sentence. Decrease in Gibbs free energy may be regarded as a measure of the net work done by the system. So, for the net work done by the system, we have to remember there has to be a decrease in the Gibbs free energy, okay, which is regarded as a measure of the net work which is done by whom? By the system at constant temperature and pressure. So there are variety of cases over here. So variety of cases. I will just talk quickly and finish this portion. Give me a few more minutes. So there are three cases when delta G is negative. Hence, a negative value of delta G signifies that the process is spontaneous. Only this much you remember. Negative value of delta G signifies that the process is spontaneous. This much. This much. Okay. This much you remember. So this is case 1. Under case 1, for a process to be spontaneous, delta G has to be negative. Okay. Less than 0 at constant temperature and pressure. Okay. Now, if delta G is 0, then if delta G is 0, a spontaneous process occurring at constant temperature and pressure attains equilibrium when delta G is 0. There is no change in the free energy of the system. So whenever there is delta G is 0, then there is no change in the free energy of the system. So remember that. Okay. So when delta G is 0, there is no change in the free energy of the system. Okay. Suppose if delta G is positive, if the value of delta G is greater than 0, that time the process becomes not feasible at constant temperature and pressure. So the reaction is non-spontaneous. So this is non-spontaneous case over here. Try to remember this also. Or directly three cases are there. I have underlined this, highlighted them. Okay, this is the third case when delta G is positive. Okay, so remember. Okay, just a second. It's not beginning. Okay, never mind. This part you can remember. Okay, now, so this is summarized over when delta G is negative, the process is spontaneous. When delta G is zero, the process is at equilibrium. When delta G is positive, the process is non-spontaneous. So this part becomes more important over here. This part, this part. Okay, just a second. What is happening? This part till here, till here. Okay, this part you try to remember. Okay, this part is very very important. Now, I think it is already time up. I have crossed the time. It is 12:03. So I would like to stop my class here only. In my next class, I'll be continuing with the prediction of the spontaneity, feasibility of a chemical reaction. Okay, so till here you please revise and remember. Okay, and then I'll continue with the prediction of the spontaneity, feasibility of a chemical reaction, and teach you some numericals based on the by using the second law of thermodynamics. Okay, so just hold on. I will first record your attendance, and then only you may leave the class after this. Okay. Okay, attendance list is downloaded. You may leave the class. Okay. Thank you so much. Have a nice day.
Thank you, sir.
Thank you, sir.
Okay.